Welcome to the Chemistry 209 Masterclass series. This series of lectures is intended to highlight the key concepts of introductory spectroscopy and structure. This lecture, Masterclass 5, discusses the basics of molecular orbital theory. Molecular orbitals can be thought of as combinations of atomic orbitals. Consider, for example, how two hydrogen 1s orbitals can combine to produce molecular hydrogen. We know that the 1s atomic orbital has a spherical electron density distribution that is most dense at the nucleus and decreases exponentially with radial distance. We can picture this as a density plot or in terms of the radial distribution. If we bring the two hydrogen 1s orbitals together, the wave function from each atom can overlap between the nuclei and constructively interfere. As a result, there is an increased electron probability density between the nuclei compared with the charge density beyond the two nuclei along the axis connecting them. This increased central negative charge density pulls the two positively charged nuclei towards one another. We might also think about this scenario in terms of the central electronic charge density shielding the two positive nuclear charges from one another. The result is a stabilization of the nuclear charge spatial configuration, which we know as chemical bond formation. This constructive or in-phase addition of the atomic orbitals results in the production of a bonding molecular orbital. One might also imagine that the two 1s orbitals can cancel out of phase or destructively interfere with one another. In this case, the wave function associated with the first hydrogen 1s orbital cancels with the wave function of the second hydrogen atom between the nuclei. At the point where the two wave functions are of equal magnitude but opposite sign, the wave functions cancel perfectly and a node, or more precisely nodal surface, is formed. This results in a decreased electron density between the nuclei compared with the electron density beyond the nuclei along the internuclear axis. The nuclei are then pulled apart by the external electron density, or alternatively, we can view the nuclei as being pushed apart by the increased nuclear repulsion. This out-of-phase or destructive interference results in the production of an antibonding molecular orbital. When combining atomic orbitals to produce molecular orbitals, we can define some rules or guidelines that should be met. First, orbitals must be physically close enough to strongly interact. In principle, atoms separated by an infinite distance can interact with one another, but wave function overlap will be minimal since the magnitude of interaction is inversely proportional to the distance between the nuclei. Of course, if nuclei come in too close contact with one another, they will repel. Thus, there is an optimal internuclear distance for bond formation that is an electronic potential energy minimum on the potential energy surface. We can also stipulate that the orbitals must combine along an axis of mutual symmetry. That is to say, the orbitals should be suitably aligned. While alignment may not be a concern for s orbitals, orbital alignment is critical for interactions involving orbitals with L greater than 0. Finally, the atomic orbitals must be similar in size and energy, which we now know are in fact related. When we say magnitude of interaction, we are referring to how much lower in energy the bonding MO is in comparison with the corresponding separated atomic orbitals. For molecular hydrogen, this is also how much higher in energy the antibonding MO is with respect to the separated AOs. It should be noted that, like atomic orbitals, for MOs of similar symmetry, the orbital with more nodal surfaces is higher in energy. This method of combining atomic orbitals to produce molecular orbitals is known as LCAO, which stands for Linear Combination of Atomic Orbitals. LCAO is often used in computational quantum chemistry as a means of generating molecular orbitals for calculating molecular properties. The importance of AO relative alignment is apparent when we think of the possible combinations of p orbitals. If we define the internuclear axis as the z-axis, we see that p orbitals can overlap in 4 unique ways. Pz orbitals can overlap constructively or destructively along the z-axis, or the px and py orbitals can overlap constructively or destructively perpendicular to the z-axis. As a rule of thumb, we find that 2 atomic orbitals will overlap to yield 2 molecular orbitals. Knowing that bonding MOs are lower in energy than the combining atomic orbitals, and that anti-bonding MOs are higher in energy, we can produce a molecular orbital diagram to describe the bonding in our molecule. For example, shown here is an MO diagram for the molecular orbitals arising from the overlap of valence p orbitals of atomic oxygen. Note that anti-bonding MOs are designated with an asterisk. The MOs formed from the overlap of pz atomic orbitals are given the label Greek letter sigma, while the MOs formed from the px and py atomic orbitals are labeled with the Greek letter pi. Also note that there are subscripts of G and U on the molecular orbital labels. These, like the Greek letters, are symmetry labels. Owing to the fact that molecular oxygen is a homonuclear diatomic, it has a center of inversion. The G and U labels describe the behavior of the electronic wave function upon inversion. If the bonding pi MO is inverted, the wave function sign changes, whereas if the anti-bonding pi MO is inverted, the wave function remains unchanged. Wave functions that change sign upon inversion are called odd functions, while those that remain unchanged are called even functions. The German words for even and odd are gerade and ungerade, hence the G and U subscripts. The origin of the Greek letter labels becomes clear when we think about the symmetry of the MOs. Notice that if we view the sigma MOs along the bond axis, the electron density distribution looks reminiscent of an atomic s orbital. Similarly, viewing a pi MO along the bond axis shows an orbital projection that is reminiscent of an atomic p orbital. It is exactly this molecular orbital angular momentum projection along the internuclear axis that determines the MO orbital symmetry. In atoms, we describe the orbital angular momentum with the quantum number L. Diatomic molecules no longer have the spherical symmetry of atoms, so cylindrically symmetric molecular orbital angular momentum projections are described with quantum number lambda. Lambda is the Greek letter corresponding to the Roman letter L. Thus, whereas atoms have quantum numbers L equals 0, 1, 2, and 3, which correspond to s, p, d, and f atomic orbitals, sigma, pi, delta, and phi MOs have quantum numbers of lambda equals 0, 1, 2, and 3. The diboron MO diagram on the left shows the MOs produced from the combinations of the valence 2s and 2p atomic orbitals of boron. As expected, the 2s atomic orbitals combine to yield 2 sigma orbitals, a bonding and antibonding pair. The 2p atomic orbitals combine to yield 6 MOs, a bonding sigma, bonding pi, antibonding pi, and antibonding sigma. Note that owing to the fact that the px and py atomic orbitals are degenerate, and because boron 2 is a cylindrically symmetric molecule, the pi MOs have 2 degenerate states. Having constructed an MO diagram, we can determine the molecular electronic configuration. We use the same build-up principle as we did for atoms, 2 electrons per MO with both electrons having opposite spin. For degenerate pi MOs, electrons prefer to remain unpaired and only pair up when a third electron is added. Thus, in the diboron case shown here, we end up with 2 unpaired or spin-parallel electrons in the 1 pi u highest occupied molecular orbital. Note that here the lowest unoccupied molecular orbital is the 3 sigma g MO, which has been shifted above the 1 pi u MO owing to an interaction known as SP mixing. If we view the MO diagrams for all of the second row homonuclear diatomic molecules side by side, the effect of SP mixing becomes very apparent. While most of the MOs derived from the 2s and 2p atomic orbital overlap exhibit smooth trends in energy variation as a function of molecular mass, the 3 sigma g MO arising from the constructive overlap of pz atomic orbitals exhibits a fairly extreme and somewhat erratic relative energy trend. In particular, we see that while the 3 sigma g MO is above the 1 pi u MO for species lighter than molecular oxygen, for O2 and heavier diatomics the 3 sigma g is below the 1 pi u MO. As a memory aid, you can remind yourself that you know where SP mixing becomes unimportant since it occurs between nitrogen and oxygen. SP mixing arises due to the fact that, like atomic orbitals, molecular orbitals can also interact with one another. For MOs to interact, they must have the same symmetry and they must be close in energy. The larger the energy separation between two MOs, the more weakly they interact. This, again, is also true of interactions between atomic orbitals. Consider, for example, the sigma g orbital arising from the overlap of pz atomic orbitals and the sigma g orbital produced from the two 2s atomic orbitals overlapping. These MOs have the same symmetry, they are both sigma g, and they are both relatively close in energy. The two sigma g MOs combine to generate two new MOs. One of the new MOs is slightly higher in energy than the unperturbed 3 sigma g molecular orbital, and the other new MO is slightly lower in energy than the unperturbed 2 sigma g molecular orbital. We can understand conceptually why this should be the case if we consider how the sigma g MOs can overlap. If the wave functions are in phase between the nuclei, there is constructive addition and therefore increased electron density between the nuclei. This enhances the bonding character of the new molecular orbital. If, on the other hand, the wave functions are out of phase between the nuclei, destructive interference reduces the electron density between the nuclei, thereby diminishing the bonding character. Note that similar arguments can be made to describe the interaction between the sigma u orbitals as well. As a result of the interaction between MOs of like symmetry, we see that the 2 sigma g orbital is shifted to lower relative energy, and the 3 sigma g MO is shifted to higher relative energy. The same is true for the sigma u bonding and antibonding MOs, but in this case the interaction energy is weaker owing to the larger energy difference between the combining MOs. Recalling that the extent to which the sigma MOs are shifted depends on how close the interacting pairs are energetically, which in turn depends on how close the AOs are energetically, it becomes apparent where the name SP mixing comes from. Owing to the fact that the effective nuclear charge experienced by the 2s electrons is higher than the effective nuclear charge experienced by the 2p electrons, 2s atomic orbitals are lower in energy than 2p atomic orbitals. The relative stabilization of the 2s compared to the 2p increases with increasing nuclear charge. For dilithium, the MOs arising from 2s and 2p AO overlap are close in energy because the 2s and 2p atomic orbitals are close in energy. Thus, SP mixing is a strong interaction. For difluorine, the MOs arising from 2s overlap are far lower in energy than the MOs arising from 2p overlap. Thus, SP mixing is a very weak interaction for F2. The MO diagram reordering that occurs between molecular nitrogen and molecular oxygen simply arises because the 2s2p energy gap in oxygen is large enough that SP mixing becomes a very weak interaction. In nitrogen, the 2s2p energy gap is small enough such that a considerable degree of SP mixing can still occur. Differences in atomic orbital energies have important bearing on chemical bonding in heteronuclear species. Consider, for example, how the 1s atomic orbital of hydrogen combines with the valence 2s and 2p atomic orbitals of fluorine to produce hydrogen fluoride. Since the hydrogen 1s atomic orbital is much higher in energy than the fluorine 2s atomic orbital, there is very little interaction between the two, and the resulting HF-MO is predominantly composed of the fluorine 2s atomic orbital. We can see this in the density plot on the right. The 2pz atomic orbital of fluorine does, however, interact strongly with the hydrogen 1s atomic orbital owing to their relative proximity energetically. Constructive overlap between the hydrogen 1s and fluorine 2pz AOs leads to formation of a bonding sigma orbital, while destructive overlap results in the formation of a sigma star antibonding MO. Owing to the fact that the fluorine 2pz atomic orbital is lower in energy than the hydrogen 1s, the bonding sigma MO has a higher relative contribution from the fluorine 2pz than the hydrogen 1s. Likewise, the antibonding sigma star MO has a higher relative contribution from the hydrogen 1s atomic orbital. In the case of the fluorine 2px and 2py atomic orbitals, there is neither constructive nor destructive overlap with the hydrogen 1s atomic orbital. We can think of this as if the constructive overlap between the hydrogen 1s and the in-phase 2px lobe were perfectly cancelled by the destructive overlap with the out-of-phase 2px lobe. In other words, the wave function overlap is zero. When two functions have zero overlap, they are said to be orthogonal. Owing to the orthogonality of the 1s hydrogen atomic orbital and the fluorine 2px and 2py, The resulting MOs arise from the unchanged fluorine 2px and 2py atomic orbitals. These MOs are said to be non-bonding. Note that the 5 atomic orbitals combine to yield 5 molecular orbitals for HF. In building up our ground state molecular electronic configuration, we find that 2 electrons occupy each of the sigma bonding and pi non-bonding MOs. Since each of these MOs is predominantly composed of fluorine atomic orbitals, we see that the electronic density in hydrogen fluoride is located predominantly around the fluorine nucleus. Thus, the fluorine end of the molecule has a time-averaged partial negative charge, and the hydrogen end has a partial positive charge. In other words, the bond is polarized towards the fluorine, and HF is a polar molecule. In some cases, the energy difference between the combining atomic orbitals is so large that the MOs produced are essentially the unchanged atomic orbitals themselves. For example, when lithium and fluorine interact, the result is essentially donation of the lithium 2s valence electron to the fluorine 2p atomic orbital. In this case, the atoms are bound by an electrostatic interaction, since the lithium center now carries a positive charge and the fluorine center a negative charge. This is known as an ionic bond, which we can contrast with the covalent bonds of homonuclear species that arise from equal sharing of electrons. Most molecules exhibit an unequal sharing of electron density that is somewhere between the two extremes of ionic and covalent bonding. Typically, we think of this situation as covalent bonds exhibiting ionic character. To characterize molecular quantum states, a molecular description of angular momentum is required. In Masterclass 4, we learned that atomic angular momenta interact with external magnetic and electric fields to lift quantum state degeneracy. We think of this interaction in terms of angular momentum projection onto the quantization axis provided by the external field. In molecules, electron densities around nuclei give rise to electric fields along internuclear axes. In this way, the orbital angular momenta of atoms couple to the internuclear axis. If we consider the simplest case of a diatomic molecule, we find that the orbital angular momentum quantum number no longer provides a unique description of a quantum state, owing to the reduced symmetry of the system. Instead, we can describe the orbital angular momentum in terms of its projection onto the internuclear axis. The quantum number that describes the projection of L onto the internuclear axis is Greek letter lambda. Precession of the orbital angular momentum about the internuclear axial electric field produces an axial magnetic field. This provides a quantization axis for the electron's spin angular momentum. Again, for molecules we find that S is not a good quantum number, and instead we describe the total spin angular momentum in terms of its projection onto the internuclear axis. The quantum number that describes the projection of S onto the internuclear axis is the Greek letter sigma. To determine the total angular momentum for the molecule, we must also consider the molecular rotation. The end-over-end rotation of the molecule generates a rotational angular momentum that is perpendicular to the internuclear axis, and therefore perpendicular to lambda and sigma. Owing to the right-angle triangle vector addition, we see that the projection of the total angular momentum J is the sum of lambda and sigma. This quantity is labeled omega. As was the case with atoms, molecular term symbols provide a succinct notation for molecular quantum numbers. The example shown below is a possible term symbol for a linear molecule exhibiting Hund's case A angular momentum coupling. We see that the superscripted value describes the spin multiplicity, which is the number of ways that lambda and sigma can couple. The central Greek letter gives lambda, the orbital angular momentum projection quantum number. Values of lambda equal to 0, 1, 2, 3, etc. give rise to sigma, pi, delta, phi, etc. molecular terms. Note the parallels between lambda and the atomic quantum number L. The subscripted value describes the total angular momentum projection quantum number, omega, which we've also seen describes how the orbital and spin momenta are coupled. Closed shell molecules are always described by singlet sigma terms. For molecules with a single unpaired electron, determining the molecular term symbol is usually fairly straightforward, since filled MOs add 0 to the lambda and sigma quantum numbers. However, care is often needed when determining term symbols for molecules with MOs that are occupied by multiple unpaired electrons. This situation arises when the highest occupied MO is a degenerate level, as is the case for molecular oxygen. Naively, we might predict a number of terms to arise from the 1πg2 frontier MO configuration of molecular oxygen, but deeper consideration of these terms shows that several cannot exist as they violate the Pauli exclusion principle. The triplet delta term, for example, requires that both electrons have identical quantum numbers. Furthermore, recalling that the triplet state spin wave functions are symmetric and singlet state spin wave functions are antisymmetric, we know that the singlet sigma minus and triplet sigma plus states also violate Pauli's principle. The methods that have been outlined in this lecture for constructing MOs for diatomic molecules can be extended to polyatomic systems. Similar labeling schemes based on molecular symmetry are used to describe polyatomic molecular orbitals, but angular momentum coupling schemes do become more complex as molecular size increases and symmetry decreases. For this reason, one often refers to the local symmetry of a bond in polyatomic species rather than specifying the total molecular orbital symmetry. This is why we refer to sigma and pi bonds in, for example, benzene, despite the fact that benzene is clearly not a linear molecule and does not exhibit sigma or pi MOs. For those of you continuing in studies of chemistry, you will see a much more detailed treatment of molecular orbital theory in more advanced courses. See you next time.